Welcome to This Explainer. Today, we are tackling a massive hurdle: how to secure maximum marks and totally avoid the common pitfalls in Cambridge Biology Topic 16.1, Crossing Over and Random Orientation. If you've been mysteriously dropping points on past papers, we're going to decode the mark scheme right now and completely transform the way you approach genetic variation. So let's start off with a really high-stakes question. Why do most students actually fail this multi-step biological pathway? Well, it's not because the biology is too complex. It's actually because of a fundamental disconnect between what you study and how you articulate it under exam pressure. You might know the textbook inside and out, but if you don't structure your response properly, your mark band just plummets. I mean, just look at this direct quote from the principal examiner reports. They said, "Candidates consistently confuse key terminology and confuse cause and effect in 16.1. You see, you aren't losing marks from a lack of studying. You're losing them from a critical misunderstanding of how examiners actually expect you to apply your knowledge. The real tragedy here is that students are doing all the hard work, but they're leaving the easiest marks on the table just by being a bit slappy with their scientific vocabulary." All right, let's kick things off with Section 1, Core Genetic Variation Principles. First up is crossing over. Now, you absolutely must explicitly define this in your mind as the exchange of genetic material between non-sister chromatids of homologous chromosomes. Top-performing students always exhibit this really connected, conceptual understanding that transfers accurately to totally unfamiliar contexts. If you just write down chromosome swap pieces, you simply won't get the mark. You have to specify non-sister chromatids and homologous chromosomes. That exact precision? That is your ticket to the top band. Okay, next we have random orientation, the independent alignment of homologous chromosome pairs along the metaphase plate during meiosis. Having this precise definition locked in prevents you from falling into the ultimate trap, which is mixing up the biological cause with its statistical effects. Think of it like this. Random orientation is the physical cause, right? And that leads to the effect of independent assortment and genetic variety in the gametes. You've got to keep cause and effect strictly separated in your written answers. Now, in just a second, I'm going to reveal a specific examiner clue that will completely change how you structure your answer. But, well, first we really need to build the technical framework that makes this clue super obvious when you're sitting in the exam hall. Moving right along to Section 2, the technical methodology. When it comes to statistical analysis, you cannot just guess which test to use. It has to be deliberate. It's basically a decision matrix. You must instantly know to deploy a t-test when you're comparing means between two continuous sets of data. Got categorical data, like, say, counting phenotype frequencies? Boom, you immediately pivot to a chi-squared test. And if you want to find a relationship between two variables, you use a correlation test. Keep this matrix firmly in your head. And when you're problem-solving practical investigations, strictly follow this deconstruct, solve, evaluate framework. Step 1, deconstruct the info by extracting data from tables and graphs way before you even look at the question. Step 2, solve it systematically. Write down every single step to secure your method marks. And Step 3, evaluate reasonableness. Actually ask yourself, do these numbers make biological sense based on the genetic principles we just talked about? Following this exact sequence guarantees you're processing the data exactly how the mark scheme demands.
Let's dive into Section 3, Evaluating Evidence and Data.
Let's do a quick autopsy on a couple of exam answers to see the difference. The flawed mindset blindly lists generic variables and just accepts data at face value, writing vague things like, "the data shows a change." Conversely, a top-band student uses comparative connectives, words like whereas, however, and conversely, to identify similarities and differences. They're actively questioning assumptions and justifying their decisions with specific data points. They'll say something like, "phenotype frequency increased by 15%, whereas the control group remained static." That evidence-based reasoning is absolutely crucial. Which brings us to Section 4, Avoiding Principal Examiner Traps. Treat this like your ultimate grade-saving checklist before you hand in that paper. Trap number 1, confusing cause and effect. Clearly state what triggers the variation versus what the resulting variation actually is. Trap number 2, forgetting to check your units and terminology. Always define terms like crossing over before you use them in extended responses, and double-check those statistical units. And finally, trap number 3, providing answers that lack specific biological context. If the prompt is about Drosophila fruit flies, anchor your answer to those specific alleles and traits. Don't just dump general genetic theory onto the page. And finally, Section 5, Final Strategy and Recap. We've covered a massive amount of ground in this explainer today, giving you the framework to avoid those brutal traps and process data systematically. But here as a final, slightly scary thought to leave you with. Literally, none of this biological knowledge matters if you misinterpret the exam paper's command words. I mean, if you describe when you're supposed to explain, you get 0 marks. So before you start writing, ask yourself, are you truly answering the exact question the examiner is asking, or are you just writing down everything you know about the topic?